Good morning, everybody. Good morning. What happened? Scared everybody? The last lecture? Yeah, right? Because it was going to be a big math day today? It's either that or the train has stopped all traffic for like 10 minutes in Fresno. It's one of those two things. Tomorrow, right? Exams come back, exam autopsy, whatever that means. Mr. Bailey, you haven't explained anything about that. I'll explain it all tomorrow, right? And you will have a full picture of what it's like to take an exam and what it means to go back and figure out the things that went right and figure out the things that went wrong. There is opportunity for redemption tomorrow, okay? And so you don't want to miss out on the exam autopsy. It's vitally important that you be there. We are forging ahead in chapter 5, right? And this is where the shoe's going to drop, right? Okay. When it comes to solving Newton's second law problems, they get big fast. So let's see what we can't work out and figure out when it comes to this. I was drawing a free body diagram of me, right, standing, okay, here on the floor. And I was trying really hard last time to get your brain to think about not the motion of things, but about how the motion's going to change. A free body diagram tells you nothing about velocity. It tells you nothing about what an object is doing, because this could be the free body diagram of a skydiver in free fall. When a skydiver jumps out of a plane, do they just kind of keep accelerating all the way to the ground? What gets in the way? The air resistance, right? The air resistance will slow them down. And they'll get to something called terminal velocity, which isn't the speed at which you die, but it's the speed at which moving through a resistive medium like air, the fastest an object can go. So this diagram right here is indicating that, so is the Earth still pulling on a skydiver? Yeah, right? And in this case, the normal force could be written instead as maybe air friction or something like that, right? It's not a contact force, but there's certainly a force up. And how do I know that the forces have to be balanced? Okay, Newton's third law says we need how many objects? 2. How many objects are in this picture? Only 1. Do we need to sing the song? If the Earth pulls on the skydiver, then where's the Earth in this picture? It's not there, right? So it's not a Newton's third law thing.
When they're equal, it means that the velocity is going to be constant, which means he's reached his max speed.
The acceleration is 0.
Yeah.
The change in motion is 0. Is my change in motion, is my acceleration 0 if I'm standing right here? How do you know?
Because your velocity is constant.
Good, excellent, because my velocity isn't changing. Some of you are like, you're not moving. And now you know that's the wrong answer, right? Okay? It's not about motion. Free body diagrams tell you nothing about velocity. This diagram is both for me standing right here and if I jumped out of an airplane and had reached terminal velocity. If I had jumped out of the airplane and was not at terminal velocity, if I was still speeding up, what would that free body diagram look like? Would gravity still be there?
Yeah.
Yes, okay. Which way am I speeding up? Which way is my velocity increasing, up or down? Down. So that means that I need force in the downwards direction. Well, if I draw my air resistance vector shorter, I can look at that free body diagram now and say, aha, I know which way this thing is accelerating. It's accelerating in the vector sum of those two forces. Remember, Newton's second law tells us that the direction of the acceleration and direction of the net force are the same. Mass doesn't have direction. So the only two things in there that have direction are the acceleration and the force. So this means that, so what direction is my force winning? Down, right? So that means that, and you don't attach this to the free body diagram. This is an added optional extra. I tend to do this just to remind myself what I'm doing. And I'll draw it off to the side. I'll draw that acceleration off to the side. Like, okay, I know that my net force is down, which means I have to be accelerating down. Okay? So on the left is a picture of a skydiver at terminal velocity, but also the picture of Mr. Balogh standing on the floor, but also a picture of my car in the parking lot. What do all three of those things have in common? There's no changing velocity, right? The acceleration is 0. And how do I know the acceleration is 0 looking at that left-hand diagram? Forces are balanced. But that picture right there for the skydiver, right, getting up to terminal velocity, shows me that acceleration is still happening. And I know that because my forces are not balanced. And that's really what Newton's second law is trying to tell us. If this isn't 0, if we add all the forces up and we don't get 0, then there is acceleration. There is change in motion. So let's draw a picture of your car on the freeway, just going straight on 41, okay? And you're not turning, you're not speeding up, you're not slowing down. What question do we ask ourselves when we try to draw a free body diagram? Do you remember? We start with a simple picture of the object. And then we've got to, in order to be able to identify forces, what question are we asking? What's pushing or pulling on the object? We go to Newton's third law because Newton's third law tells us that two objects have to be interacting. We want to avoid these fictitious forces, right? These forces that we kind of make up because we think we know what we're doing. And the way we're going to be safe is by asking, what are all the things, the other objects that are pushing or pulling on this car? Are we going to draw those other objects? No. Free body diagram is about the central thing, in this case, the car. But we're going to ask the question. We're going to apply Newton's third law. Newton's third law tells us that forces always exist because two objects are interacting. So what objects are interacting with your car as it drives straight and level down the highway? Air resistance. So the air is pushing against the car. So how do we want to so this is where it gets a little bit squirrely because we do kind of have to make an assumption or a guess as to which way this car is going. Even though free body diagrams don't tell you anything about motion, we know that air resistance always acts which way versus the motion? Against it, right? So if I'm driving positive X, right, which way is the air resistance going to be? Negative, right? So we'll just assume that it's driving to the right, even though this diagram doesn't tell us anything about that. So there's the air resistance, okay? So the Earth, we always call it gravity, but the object is the Earth, right? And the force is gravity, which is the weight of the car. What other objects are interacting with the car? The ground, okay? Now, this gets, again, a little bit hairy, right? We know, since the car is traveling at constant speed on a level surface and not turning, what do we know about the acceleration? It's got to be 0. So what does that mean the free body diagram needs to have? In all directions.
Equal forces.
Totally equal and balanced forces. Is this balanced yet? No. So we need to be careful. We know that there needs to be some force to counteract gravity, right? In order for the acceleration to be 0. But make sure that you can tell me what that object is. What object is causing that uppy force? The ground, right? We give this a special name because the car is in contact with the ground. We call that a normal force. All right, are we balanced yet? No. What direction do we need a force in? Do we need something to the right, don't we? Okay, we need something to the right. approximately as long. So I know that it has to be there because, again, I'm going for an acceleration of 0 in this case. So what object is making that? What's pushing or pulling on the car to the right? Okay, like the motor, the gas. I mean, technically the friction between the tires and the road. Okay? But you're able to like realize that the motor is pushing the car forward, right? Okay? So we've given that thing an object. I'll just call it the motor force. I don't know, whatever. Okay? Right? Now, these free body diagrams, all three of them are not complete. There is one key thing that is missing on all three of these free body diagrams. And I will come after you and I will ask you, like, where is this? If you ever hand me a free body diagram to check, you do need to specify which way you are calling positive. You need to provide a coordinate system for reasons that are going to become apparent in just a second. Okay? So for me, standing on the ground really doesn't matter. Okay? When the acceleration is 0, you pick whatever you want. Okay? There's easy ways and there's hard ways. I would call up positive y and to the right positive x, sort of like a standard coordinate system. Okay? But let me give you a rule of thumb that on the surface seems like it's going to be more difficult, and it will feel more difficult at first, but is going to make things so much easier in the long run. And this is something we do all the time in physics and engineering and STEM fields. We are free of the world and society telling us what to do. And by golly, we're going to do what we're going to do. Always pick a positive direction that's the same as your acceleration. What direction is the acceleration in this second diagram? Down. So which way is positive y? I don't feel comfortable, Mr. Balogh. Wait, down is positive? Yes. I'll show you why later. I'm just telling you right now that the safe thing to do is to call that positive y. Does x matter in this diagram? Are there any x direction forces going on? No. Okay? And again, for this car one right here where the acceleration is 0, it really doesn't matter which direction I pick to be positive, but you do want to try to line up your coordinate system as much as possible with the forces that you have. Since all my forces here are up and down, left and right, I'm just going to pick the standard one again. That's fine. But what happens if you hit the gas on your car and you start speeding up? Does that change the normal force? No. Does it change gravity? No. Does it change air friction? Maybe. Okay? So the normal force stays the same. The gravity stays the same. The air friction might do something. But importantly, if this thing is accelerating to the right, speeding up, right? Okay? What do I have to draw for this motor force? I have to draw a longer vector, right? I've got to graph it, like I have to visually represent that, okay, now I know there's an unbalanced force. We've hit the gas, we're speeding up, right? And so now what direction is my acceleration? It's to the right. And so which way am I going to make positive x? I'm going to make it to the right. And whatever you choose for one, the other one has to be 90 degrees to it. Okay? No fair making positive x to the right this way and then positive y in some arbitrary direction, right? It either has to be straight up or straight down. Okay? So why am I harping on about this? Well, what happens if we hit the brakes in the car? Well, now we've added brakes, right? So it's not just air resistance, right? We got the air resistance. We're still moving. Which way are we still moving, by the way? We're still moving positive forward, right? But now we've added brakes. Hopefully we don't have any more motor force. Don't hit the brakes and the gas at the same time. It's bad for your car, right? Which way is this thing accelerating? To the left. How can you tell it's accelerating to the left? There's things pointing to the left and nothing pointing to the right. So it's accelerating to the left. Which way are we going to call positive x? We're going to call it to the left. We can still make positive y be straight up and down, right? But we're going to go with the direction of the acceleration to be safe. Because if you don't, you're going to miss some minus signs and you're going to be hating life, okay? For the car hitting the brakes, I can't stress enough. Does that diagram tell you anything about how that object is moving? Can you just look at that and tell which way it's going? Some of you want to say yes. The answer is no. It tells you nothing about motion. Okay? It tells you everything about how the motion is going to change. So if this is an object, that your car moving to the right that's hit its brakes, we know it's going to accelerate which way? To the left, which means it's going to speed up or slow down? Slow down. Okay? That could be the free body diagram of a car going in reverse. Right? Which way is a car changing its motion when it's in reverse? It's changing its motion in whatever the reverse direction is, right? Which means it's speeding up in that negative direction. Be careful. It's easy to think that the free body diagram tells you something about motion. It tells you how the motion is going to change.
Wouldn't the air resistance tell us about its motion?
Yeah, the air, we haven't done friction yet. That's next chapter.
Oh, okay, I'll just ignore that.
If we know it's decelerating, then wouldn't we want the acceleration be negative in this case? Because, like you said, we could find out if we could reverse.
That is a perfectly normal thing to think. The problem in your statement was the prefix you put on the word acceleration. I know you want to live in the world where deceleration happens. Okay? It's all accelerations. Whether it's speeding up or slowing down, a car that has slammed on its brakes is accelerating. Again, the misconception is that acceleration means to speed up and deceleration means to slow down. As soon as we start doing acceleration, deceleration, negative and positive sort of become arbitrary and it gets messy. Okay? So physics is nothing if not precise, okay, in the language that we use. So yeah, in common usage, is the car decelerating when it slams on brakes? Sure, right? But I would still make the directions of my forces follow that acceleration. Again, to confuse some minus sign issues. All right. Where does all this come into play? Where does the rubber really meet the road? Let me show you. What if we had, I don't know, a ball rolling down a hill? What direction does gravity pull on the ball? Down. Straight down, right? Okay. So we have weight. What direction is the normal force in this case? Remember why we use the word normal? What does normal mean? Perpendicular to the surface of contact, right? In this case, the ground of the hill, right? So what direction is perpendicular to the hill? Yeah, is it straight up? It's kind of diagonal, isn't it? It's this way, isn't it? Okay, for a ball that's just sliding, rolling down a hill with no friction, let's ignore the air, let's keep this really simple, okay? Which way is the ball accelerating, changing its motion, speeding up or slowing down? Okay, if we let it rest, right, we put it on the top and we let it go, we know it's going to speed up which way? Down the slope. So which way is our acceleration? It's down the slope, isn't it? So which way are we going to call positive? Down the slope. Wait, Mr. Bailey, you're telling me that I have to put positive x like this? That's what I'm telling you. If you pick positive x down the slope, automatically, what direction does y have to be? Perpendicular to that, right? It could be away from or into. We'll do away from. Okay? But that becomes my coordinate system, and now we are in a realm where positive and negative directions are up to us, and that's why it's important that you define what directions you're calling positive and negative. Because if you don't, you're going to be at sea with no directions to obey. Always pick your a positive direction, x or y, to be in the same direction as the acceleration. This does a couple of things, which you're not going to appreciate till later. But I'll tell you right now, and then I'll remind you as we go through and I'll point it out. It saves you from a minus sign error, and it simplifies your vector components. I just said two very bad words. What did I say? Vector component. Are vectors back?
Yeah. I've been saying that the entire time.
Did they ever leave? I mean, we did vectors in chapter 3, right? And we did them a little bit in chapter 4. We had to break up the x and y components. It was kind of easy because like x is always cosine, right? Newton's second law. How many equations are on the screen? 3.
Acceleration and then force.
There's 3 equations right here. What 3?
Your vector A and vector force. What are you calling it?
There's 3 equations right here. There's one in x, there's one in y, and there's one. Oh, Mr. Balogh. I was already having a bad day this morning. Could you just not make it worse? No, I'm going to make it worse. Well, I'm going to make it better. We're not going to do z. We're just going to do x and y. Okay, right? But this is a vector equation. It grows. Okay? It becomes ma sub x equals sum of the forces in the x direction. And ma sub y equals the sum of the forces in the y direction. And what was one equation becomes 2. And if we do it in 3 dimensions, 3. And by making sure that we always point a positive direction in the same direction of acceleration, what do I guarantee about the acceleration in the other perpendicular direction? It's going to be 0. Did you catch that? If I align my coordinate system so that I point my acceleration to be positive in the x direction, that means the acceleration only exists in the x direction. What will the acceleration in the y direction be? 0. And I just saved you from having to find a component of acceleration. What if we set positive y to be in the same direction as the acceleration? What does that guarantee for the x direction? 0 acceleration. So we're saving coordinates there. Right? We're saving, not coordinates, we're saving having to find vector components. Remember cognitive load? We want to lower cognitive load as much as we can. This is one way we can do it. I know you don't understand why I'm teaching you all this stuff right now. So what I want to start doing, want to talk about like the problem solving process, specifically for Newton's second law, and then we're going to do some examples. We're going to do some examples, we're going to do a quiz, we're going to do some examples, we're just going to start applying all of this stuff, okay? And see as I model it and you start getting used to why we're doing it the way we're doing it, you'll find some methodology that will work for you. This picture is here for a reason. Just to reiterate a couple of things. It's okay to put an acceleration vector on your diagram. It's not required. It can be helpful as you go back later and like, what's going on here? Oh yeah, I thought acceleration this way. That acceleration vector is often a guess based on what's going on in the problem. But you never want to attach it as a vector to your object. Okay? What's the only thing we attach to our object in a free body diagram? Forces, right? We only want to draw force vectors. An acceleration vector can be there, but leave it off to the side. Never ever do you want to write a vector that says MA on it. Again, this is that misconception that comes from the way Newton's second law is often taught, where force is a mass times acceleration. It's not. Okay? A force is a push or a pull. Mass times acceleration come together with those forces to tell us what the object is going to do in terms of its motion. But like an MA, name the object that causes MA. The Earth causes gravity, right? That would be mg. What mass are we talking about? The object's mass. But can an object exert a force upon itself? No, right? And so it's just wrong. Okay? There's never going to be any MA vector on your diagram. Okay? So just some trying to throw some of the bad water out and get some good water in. Okay? So let's practice. Okay? Draw me in your notes right now. Just draw me a free body diagram of, I'm going to use the word athlete. I'm no athlete, right? Just jumping off the ground. Okay? I want you to draw them jumping off the ground, not when they're off the ground. Because when they're off the ground, what is their state of motion? Free fall. Right? Okay? Don't draw me that picture. I want you to draw me the picture of the athlete as they're coming like up off the ground. Still in contact with the ground, but changing their motion. Be thinking about all the objects that are pushing or pulling on the athlete. Think about which way the athlete is changing their motion. Make sure you have a longer force vector in the direction of the change of motion. All right, you got something on your page or your iPad or whatever? Okay. Without words, just smile to the person next to you and hold up your picture and show them. Just hold it up. Just hold it up, right? No comments. Just hold it up. And then look at theirs, right? Okay? All right. So, what shape do we draw? Circle or a square, doesn't matter. Okay? What objects are pushing or pulling on the athlete? Which is a force. Earth is the thing that makes it. So I identified the object, know what the force is. Okay, what else? The normal force. But how am I going to draw the normal force? Longer. Why? Which way is the athlete changing their motion? Upwards, right? Is this free body diagram complete? No. What's missing? Coordinates. Which way are we going to call positive? Up. Why are we going to call positive up? Because the acceleration is up. That would be a complete free body diagram. How'd you do? Did you forget your coordinate system? Yeah, pretty easy to do. Great. Very first baby steps here. How many of you struggled with like which way to draw the forces? Yeah. Okay. So how do you get used to this stuff? Practice. Practice, practice, practice. Okay? Quiz each other. Draw me a free body diagram of a person walking. Draw me a free body diagram of a car. Draw me a free body diagram of a bird. Whatever, right? And it doesn't matter initially whether you're getting it right or wrong. The point is that you're practicing, you're starting to think about forces and all that kind of stuff, right? I'll be blunt. I noticed that a good 60% of the class would wait until the day before the homework was due to start the homework on the first unit. I can see some of the smiles out there. Okay, right? A day is not enough. It just isn't for your brain to get used to this way of thinking and drawing and all that kind of stuff, right? Every day. Even if you can't dedicate that day to physics because you got math or chemistry or something else, right? Take some 15 minutes and practice something. And then the next day when you can dedicate a lot of time to physics, dig into it, right? But don't wait. Don't wait. Okay? And how did I know that about you? 60% of you? Okay. On the back end, I get all the data. So, yeah. Get ahead of this. Really get ahead of this. Okay. Draw that free body diagram. We did that one already. Yeah. Why is this? We did this one already, didn't we? Okay. Let's not do that one. Okay. Two of them now. A skier sliding downhill and then another one of the skier sliding uphill. Like maybe the skier was sliding down a hill, got to the bottom, and then there was a jump or something, right, that they're about to go off of, right? But I want you to draw a free body diagram of them sliding down the hill, and then the free body diagram of them kind of starting to go up a hill. If you get stuck, turn to each other and help each other. Feel free to share and look and talk and work this one out. If you're feeling stuck or not sure right now, you should be turning to each other and holding it up and going, look, what did I do? Okay. How was that? Not sure if I got it, all that kind of stuff, right? Okay. Well, did it help to talk to the person next to you and bounce ideas back and forth? Yes. I like it one way, I think. Okay. Use that. Right? You are your best resource. Okay. Each other. I'm going to, let's, okay. Do we know something? Do we know the acceleration? Which way is the skier changing their motion on the downhill? Down the slope, right? Speeding up? As they say, okay, so I'm gonna go ahead somewhere and I'm just gonna draw, just put it over here. And then up the slope, which way is their acceleration? Up the slope? Down the slope? What are they doing as they go up the hill? They're slowing down. They're moving up, but they're slowing down, which means the acceleration is which way? Down. Oh my gosh, Mr. Balogh, I had to remember chapter 2 stuff? Well, yeah. Okay. All right. So we got that. All right. So what does that mean for our coordinate system for the downhill picture? Which way is going to be positive? Down the slope is going to be positive. Positive x that way. Which automatically means positive y is either directly away from the slope or directly into the slope. Okay. Now that I know my coordinate system, now I know my acceleration, I'm going to ask the question, the magic question when I go to identify forces. What's the magic question? What objects? Yeah, identify all the pushes and pulls, but if you're going to draw a force, make sure you know what object is causing it. So, what objects are interacting with the skier? The ground. Okay, when you say the ground, are you meaning like the earth pulling on them or like the surface of the hill? Surface of the hill. So what's that force going to be called? Normal force. Okay, points perpendicular surface. Okay, we already talked about the earth, so we'll just get that one in there. Okay, any other objects interacting with the skier as they slide down the hill? Okay, so for chapter 5, there is no friction. Chapter 6 is where we'll bring friction into the mix, okay? So for now, we are not going to think about friction, okay? That's the friction of the snow on the skis. That's the friction of the air. We're skiing on the moon on ice or something. I don't know, okay? Why are we doing this? Why are we throwing away some of these things? We want to start with the basics. And it might seem like, oh, that's not real and that's stupid and you guys never do. Fair, fair. But friction is hard. Okay? Friction, you'll see next chapter. Okay? All right. So if there's no friction, are we done here? Are there any other forces? Yeah. Yeah. Where's the force pushing it down the hill? Name the object that is pulling or pushing the skier down the hill. What causes things to roll downhill? The earth, gravity pulling on it. Is gravity already on the diagram? Yes. Do I draw another gravity vector? No. What's going to happen, preview, is that we are going to have to divide the gravity vector up into components. And is there a component of gravity that points down the hill? Yes. But we're not going to go and draw a new vector there because there isn't another object. Getting a little bit ahead of myself there. Okay, diagram of the skier sliding up the hill. What direction is the positive x-axis? Down the slope. Okay, is normal force still there? Is gravity still there? Are there any other forces? Are there any other objects? Has anything changed? No. It's exactly the same diagram with the difference that our positive direction is now backwards. how badly do you want to like draw that force that's acting down the hill or the force that's acting down the hill? Wait, gravity acts down the hill in both cases? Well, yeah, because which way does gravity point? Down. There's going to be a day, there's going to be a moment when you draw me a vector and then you're going to say gravity's pointing up the hill. And I'm going to be going, what are you doing here? And you'll be like, what? I said, gravity points up, and you're just going to look at me and go, Mr. Balogh, you have driven me to the point where I don't even know which way gravity points anymore. Welcome to my life. Okay? That's normal. That's a thing that happens, right? You got to step back and you got to realize, oh my gosh, gravity doesn't point up the hill, it points down the hill. Okay. So let's talk about the problem-solving process and really just get into some examples here. Okay? Can I take my hat off or is it good? You like the hat? Okay. It gets sweaty under there. So remember, visualize, strategize, do it, check it? This is the same overarching strategy. It's just now, take a stab at what our visualization is going to be. It's going to be the free body diagram, right? We spent all of that time teaching you about free body diagrams for a reason. Okay? It's not because I'm good at art. Okay? It's because it's an excellent, excellent analysis tool. Then our strategy is to use that free body diagram to write down Newton's second law. There is one toolbox equation for this chapter and the next. That's it. Okay? Which is a bit of a lie because it's really two toolbox equations, isn't it? Or three if we go in the z direction, right? But as far as like the toolbox is concerned, that's your only tool. Everything else comes from a free body diagram and a lot of math analysis. And you're sitting here going, Mr. Balogh, this can't be that bad. One tool? This is great. I could never guess wrong on which tool I need for my toolbox. True, but do you know how to use the tool? Right? That's where it's all going to come down to. And then we'll do the math that falls out of applying this, and then we'll try to find some way to check it. So I want to, as an example, solve every problem that involves any object going up or down a hill. Like, this could be our skier, it could be a car, it could be anything. This is a choose your own adventure day. Give me an object that you would like to slide down a hill. A very icy, frictionless hill in space. Oh, jeez. Okay. It's been a while since that one got thrown out. Okay. Let's not do Mr. Balogh.
My cat.
Your cat? Do you like your cat?
Make-believe cat.
Make-believe cat. Schrodinger's cat?
Sure. Tomato again.
Oh, that's right. We had the tomato last time, didn't we? That would make sure that PETA doesn't come after me. Right? The Society for the Ethical Treatment of Hills requires me to tell you that no hills were harmed in the creation of this example. Should we do the tomato? I mean, I don't want anybody to think we don't like cats. But tomatoes?
Yeah.
I like tomatoes. Tomatoes don't like me anymore after like 44 years old. It's kind of weird. All right. But I really like tomatoes. So, the inclined plane. This is a category of situations, problems, okay, where some object is on a triangle. This is what hills look like for you now in physics, okay? If something's rolling up a hill or rolling down a hill, it's rolling up and down a triangle, okay? We represent the hill like now. We are going to get crazy shaped hills. That's chapter 7 and 8. Okay? But for now, nice, even, straight hills. Okay? This could be your driveway. It could be a loading ramp. It could be a ski lift. It could be a hill. It could be a mountain. The general idea here is that we've got an object on a tilty surface. Okay? That's what we mean by inclined plane. A plane is a flat surface. and then we incline it. And typically when we incline it, we know the angle of incline. Sometimes problems will try to mess you up by giving that angle in a different spot, but really you want to use some geometry, make sure you get that angle right there. Okay, then we drop our tomato on it, right? There's our tomato. Okay, and we've already drawn this picture, so I'm going to go kind of quickly because it's the same as the skier picture. Okay, so I have the surface itself, the contact between the tomato and the surface, the normal force right there, and then I have the force of gravity acting directly downwards. There's no friction in this problem, and there's no other objects that are pushing or pulling on this tomato. I've got the hill, and I've got the earth. That's it. I'm going to make the assumption that it starts at rest and speeds up as it slides down the hill. So my acceleration, my changing velocity will be down the hill, which means I am going to go ahead and define positive x as being down the hill. I'm trying to give you an algorithm, a method, right? And as you go back and review your notes and maybe watch the YouTube video, write down like these steps. Like my steps should be, right? Draw a free body diagram, okay? Get the coordinate system and accelerate, right? Okay? Try to go through those steps because they'll help orient you. This is how we're organizing our information and doing our analysis. Okay, even though notice there's no numbers in this problem. Okay, like I said, I want to solve all the problems. Okay. Is this a complete free body diagram? Yeah, but so we'll just say that theta is given and that the mass is given. Okay, but like as far as the diagram is concerned, do I have labeled forces? Yes. Do I have a coordinate system? That means it's complete, right? The acceleration's an added extra. Whether or not I have all the forces is up for grabs, but Mr. Balogh said that if I try to think of all the objects that are pushing or pulling, I've got a good chance of getting it right. It's what you go wrong when you start inventing forces and not identifying objects. Right? Okay, so second step in the problem. So we drew the free body diagram. We identified and labeled the forces, right? Strategize. Find what? Components? Oh no. Find components of forces not oriented along a coordinate axis. Okay, that's fancy words for one of these forces is not playing nice. It's gravity. What's wrong with gravity? It's not on X and it's not on Y. The normal force is lying along which axis completely? The y-axis, right? But mg is not, like, my axis is pointed, right? And so that means that I need to go find the parts of gravity that point along the x and y axis. Positive or negative, whatever they are. I should mention something really quick. Has anybody noticed that I've broken a rule? No, not yet. I did. The rule I broke is that this kind of isn't really a free body diagram anymore because I got the hill in the picture. Right? Free body diagram is supposed to be just the tomato all by itself. I have noticed over the years, personally and in my students, that it can be a struggle. If you take this tomato and just tried to draw it in space and then start doing all of this, it can be awkward to figure out where angles are and things like that if you don't have that triangle right next to it. So yes, technically this is just a free body diagram. I'm only drawing about the tomato, but I leave the hill in the picture to orient myself, right? To make sure I remember that there's angles and things. So one of the things I like to do is I go in and I do like to draw sort of right on the top of my tomato or my object. I like to draw just a very faint coordinate system, right? lined up with what I've said my x and y coordinates are. This helps me, again, visualize better, okay, what's going on here. This means that there are components of mg that lie along this axis. Remember, a vector's components form a right triangle. The vector itself is the hypotenuse, and the components are the adjacent and opposite sides of a triangle. Which way does mg point when it comes to the x-axis? Up or down the hill? It points down the hill. Which way does mg point along the y-axis? Into or out of the hill? Into. If I put those two vectors together, if I go down and into the hill and then I go down the hill, do I get mg? Yes. If I go down the hill and then into the hill, do I still get mg? Yes. We're just finding along the x and y axis the components of that mg vector. Do you guys mind closing the door over there? Got noise out there. Okay. Now that I've identified where the components are, I need to find an angle to be able to work here. And believe it or not, you already know what angle is sitting right here. What is it? It's theta. I didn't know that, Mr. Bale. What do you mean I already know that? You've done this problem. That's a bad pen. Where have you seen that? Very first lab? Now do you know why I gave you that problem? Maybe. So I didn't have to explain it now? We discovered in that lab that these two angles are what? They're identical, right? So if you know the angle of incline, then you also know the angle that's sitting right there. It's theta. Which means that the component of mg that's pointing down the hill is going to be sine or cosine? The one that's pointing down the hill. Is it touching theta? This one right here. Is that one touching theta? No. Therefore, sine. It's all coming together. Okay, the one that's pointing into the hill, along the thing we're calling the negative y-axis, is it touching theta? Yes. Therefore, cosine. Is there a method to Mr. Balow's madness? It's mad. It's mad. Okay. So what we've done here, okay, we drew the free body diagram, and then we went and we found components that weren't on a coordinate axis, right? It was mg that didn't lie only along x or only along y. And so we found its parts that do lie only along x and y. With all of that set up, we are now empowered to write down Newton's second law. Is that light flashing or am I having a stroke? Okay, it's flashing. It does that, doesn't it?
Yeah, that's why we like fluorescent lights.
Yeah.
They let us know when they're dying.
Say we go back to candles or something. Anyway, okay. So we have two directions to work with here, right? We have an x direction and we have a y direction. And so in both of these directions, I'm just going to start with MA and X equals, and then an MAY equals. I'm giving you a template here. Okay? This will always be the same, regardless of what the problem is. You're going to start with MA equals, and then you're going to start digging into the forces. I told you when I taught you about it that I like writing it backwards, right? I like the MA first and then the forces. Because over the years I've noticed that when students dig into the forces, you tend to be good about identifying force component, all that kind of stuff. And then the student will sit there and go, now what do I do? Because I've got a bunch of forces, but I don't have any equation. It's got to be equal to something to be able to get any traction with it, right? If you get the MA out of the way first, MA equals, just get it down. Then you can concentrate on the forces, and when you're done, you will have math to work with. You're less lost. Okay, so MA equals, X and Y directions. On the other side of that equal sign, we are going to write down all the forces that are only along the X direction. Look at the diagram. How many forces lie along the X direction? Just mg sine theta. Do you see it? Mg sine theta is the only force that lies along my x-axis. So I'm going to write down mg sine theta. And then I'm going to go and I'm going to ask mg sine theta, what direction are you pointing? What direction is mg sine theta pointing? Down the slope, which is also the positive direction. Oh, you guys are so good. And you're going to put a positive on there. You're not just going to leave it blank. You're going to put a positive on there, which is you worked hard for that information. You applied concept. Write it down. Okay. Are there anything else? Are there any other forces in the x direction? No. You can come over here and like put a check mark on it, right? Like, I got that one, right? Okay, just to, I'll leave check marks off, but you might want to come up with a method to just check to make sure you got all the forces off your diagram. Okay, MAY. In the Y direction, how many forces are there? There's two. I'm looking at this Y axis. And I've got what looks like normal force, leave a space, mg cos theta. Now what are we going to go do? What sign? What direction? So for the normal force, positive or negative? Why? Because it's along the positive y-axis. Okay. Mg cosine theta? Negative. Why is it negative? It's pointing on, it's on the y-axis, but it's pointing into the hill, which is the way we called negative. Okay. We did that. Write down the second law equations. Do it. Do what? What can we solve here? If we know the mass and we know the angle, what can we solve for that's unknown? The acceleration. Right? Let's find out what the acceleration of this tomato is going to be if it slides down a very icy hill in a vacuum. All right? Oh my gosh. There's two equations here, right? And I got to solve for both accelerations, AX and AY, and then like put them together. Oh, wait a second. I already know what AY is. It's 0. Why is AY 0? Because the rule of thumb forced it to be so, right? We paid the price of having to tilt our coordinate system, right? But in doing so, that lets me come over here and go, and now I've got a 0 on this side, and I have an n minus n. So that tells me my normal force is equal to my component of gravity that points into the hill. Does that tell me anything about my acceleration? No, that was pointless math. No, actually, it wasn't pointless math because it's going to come back to get us in chapter 6. I should probably not say things like that. All right. The x direction equation is mathematically, how do I solve for the acceleration? Well, I can get rid of something first. The mass. Oh? Wait a second. Are you trying to tell me that it doesn't matter if this is a tomato or a cat or an elephant or anything else? What? Why would the mass not matter? What's doing the pulling? Gravity. What does gravity do? Accelerates all objects at the same rate regardless of their mass, right? Gravity pulls with different weight, but it always makes sure to accelerate things at the same speed. So is it any shock that if gravity is the only thing acting on this thing as it rolls down the hill, that we would get the same answer regardless of what the mass is? In other words, if we go out and we drop an elephant and a mouse off the building, which one's going to accelerate more? They accelerate at exactly the same rate. It's because we're ignoring friction. Yeah. Physics land. Don't worry. You guys are going to beg for mercy when I throw friction into the mix. You're going to be like, can we please go back to physics land? I'll be like, no. You guys wanted it real? I'll give you one semester. My students were really on my case one day, and they're like, Mr. Bailey, you always throw friction. Okay, fine. And I turned around and I started doing like the trajectory of a ball through the air with air resistance and like the ball having English and spin on it and all that kind of stuff. When I had ripped out my like fourth differential equation, okay, and was kind of starting to get into something called Hamiltonian mechanics, they begged for mercy. They're like, Mr. Bailey, we've never seen math like that. I know you've never seen math like this, but you said you wanted to see the truth. You can't handle the truth. Anyway, all right. So, this is what we got. If we had numbers, we could put numbers in, right? But I did this without numbers because I wanted to solve all the problems, which I did, okay? But now we have to check it, right? It's that step everybody loves to forget, okay? And I don't have Wiley Plus to back me up here. ChatGPT is not going to help. So, A equals G sine, what is that? How do I check that? Play with it. Push it to its extremes. Make it scream. What do I mean by that? What are some extremes? What are something I could play? Can I play with little g? Can I change that? No, this is what it is, right? It's a constant, 9.8, right? But what's the thing I can play with? The angle, right? And what are some values for sine and angles that I know? Like, what's the sine of 0? You had a 50-50 chance. It's 0, okay? Sine of 0 is 0. 0 times 9.8 is 0. The acceleration will be 0 if what is true? What does an angle of 0 look like? A flat surface, right? You put a tomato on a frictionless surface, is it going to go anywhere? No. Okay? Do we expect the acceleration to be 0 if it's just sitting on a flat surface with nothing to push or pull it? Yes. The gravity and the normal force would cancel each other out. We're done here, right? Okay, what's the other extreme? 90. Ooh, what's the sine of 90? 1. It was your other guess. And 1 times 9.8 is 9.8. We know something special about an object when it's accelerating at 9.8. What's it doing? It's in free fall. What does my hill look like with an angle of 90 degrees? A frictionless wall. And if a tomato is sliding down a frictionless vertical wall, is it in free fall? Yes, because there's no more normal force and gravity is the only thing acting on it. Taking this thing to its extremes tells me in that behavior that it seems consistent for the extremes, so I can take a really good guess and say, well, somewhere in between, is it going to be right? Yes. I pushed it to extremes. It worked out. That's going to be the acceleration of any object going down, sliding down a hill, right? If gravity is the only thing pushing on it. The thing in the box is not a toolbox equation. Part of the roughness of chapter 5 is that you need to develop equations. Your toolbox equation is ma equals sum of the forces. But you will be deriving equations in every problem. Don't try to apply. I mean, if you've got another problem where the object is just sliding down a hill with no other forces, is that going to work? Sure. But the thing that you are going to live and die on is your ability to set up and develop these problems. Okay? So, and I'm going to be a mean teacher in that I am going to be looking for your ability to communicate to me that you know how to develop and think through these problems. It's not enough to get the answer. I have to know where it's coming from. And so it's important that you spend the time to work out this method, right, of developing equations and not just relying on, oh, that one's in the box and I can apply it to everything. That is simply not the case. Let's do a quiz.